In this module, we will deal entirely with gases. This first section is about properties and movement of gases, and you have already been able to identify things that are in the gaseous state. We've encountered them a little bit. They've certainly showed up in reactions, but this section will be way more in depth about how gases move, their properties, and then how do we do calculations when they are in a reaction. So for a gas, we have widely separated particles and lots of free volume or lots of empty space. We typically measure pressures of gases. So for pressure, we're looking at a force per unit area. And the standard units are atmospheres or ATM, where a normal pressure is 1 atmosphere. That's like kind of, like the average on Earth pressure that we're used to existing at. The other pressure units you're going to see are millimeters of mercury, torr, pascals, psi, and you will be given conversions for these. So conversions, 1 atmosphere is the same as 760 millimeters of mercury, and that's also the same as 760 torr. So 1 millimeter of mercury is equal to 1 torr. And also you'll see for an atmosphere, it is the same as 101,325 pascals. And 1 atmosphere is also the same as 14.7 psi. So psi is probably what you are used to seeing in kind of just normal settings, right? That's the pressure that you might measure the air pressure of your tires in. Okay, so for a gas, we can have a density of a gas, and we have dealt with densities of solids and liquids. For the density of a gas, it is highly dependent on pressure and temperature. So you will see those as a part of how we can calculate a density. The values are typically small, so we tend to measure and report in grams per liter instead of grams per milliliter. The equation that you would use is that the density is equal to P times M over RT, where P is the pressure in atmospheres, M is the molar mass in grams per mole. R is a constant. This is the gas constant, the one that we need. There are a couple of versions, but the one that has the units we need is 0.08206 liter atmospheres per mole Kelvin, and then we need the temperature in Kelvin. So if you go through and cancel all of this out, you'll see that the units you would get out of this are grams per liter. Now, if we're under STP, which is just an abbreviation meaning standard temperature and pressure, which means 0 degrees Celsius or 273.15 Kelvin and 1 atmosphere, you can do that the density is the molar mass over the molar volume, where the molar volume is 22.41 liters per mole. That value is going to come up again in a little bit when we talk about ways of treating and models of treating gases, but that is one way to calculate density is the molar mass divided by 22.41 if you're at 0 degrees and 1 atmosphere. Regardless of the temperature, though, you can always use that density equals PM over RT. Something special about the behavior of gases, there are different ways that we describe how they move and talk about what it means. So diffusion is how a gas spreads in response to a concentration gradient. Now, this is, right, like your intuition here should work. It travels the way that you would expect in that it goes from a high concentration to a low concentration, or essentially it is moving in a way that equalizes the concentrations. And the rate of diffusion depends on the molar mass. Heavier molecules move more slowly. So move slow if it's heavy, moves fast if it is light. And we'll have a better connection and relationship for that in a bit. The other movement of gases that we will look at is something called effusion, which is how a gas escapes from a container through a small hole. So the rate of effusion is proportional to 1 over the square root of the molar mass. And it will still give you the same idea, which is that if it's heavy, it moves more slowly. If it is light, it moves faster. Now, you can relate this like one gas to another, and it's been put together as Graham's law of effusion. So if you know the rate of one gas or the ratio of the rates even, you can find out information like molar mass, because the rate being proportional to 1 over the square root of molar mass means that we can write this equation. And let's do an example. So the example says an unknown monoatomic gas effuses at a rate of 0.462 times that of N2. Identify the unknown. So we're back to, it feels like this problem has absolutely no information. How do I solve it? Well, we have our keyword of effusion, so we can use Graham's law of effusion. So we're not given rate information really. We're giving the rate relationship. So the gas effuses at a rate 0.462 times that of N2. So I don't know, you can maybe come up with this faster than I did, but I started by writing the rate of the unknown is equal to 0.462 times the rate of N2, which is exactly what the sentence said. Now, that in that form won't go into my equation, but if I divide both sides by the rate of N2, then the ratio, the rate of my unknown over the rate of N2 is equal to 0.462. So now I have, if the unknown is A and N2 is B, I have the left side of this equation completely set up. I do know the molar mass of N2 gas. Now I did have to calculate this because there are 2 nitrogens, but it should be 28.02. And now I know everything except for the molar mass of my unknown. And my molar mass of N2, I can put this in, really in any units that I want. I will just get the same unit back out for the molar mass of my unknown. So I'm going to leave this in grams per mole. So 0.462 equals the square root of 28.02 divided by the molar mass of the unknown. I'm going to start by squaring both sides. So 0.462 squared will equal 28.02 over the mass of the unknown. And if I rearrange this a little bit, I end up with 28.02 divided by 0.462 squared. And this would be 131 grams per mole. Now, the only reason that I can then go identify this is because I'm told it's a monoatomic gas. So that means I can just go look for a molar mass of 131 in the periodic table. And if you do this, you will find that xenon has this molar mass.